Welcome back to Math 451. We're now entering into section 4.3, in which we are going to apply the definition of a derivative directly as our numerical method. Numerical differentiation as a subject alone, without any other intended purpose, may be pretty pointless. Now, why is that? The reason is that it's just not hard to differentiate about any function that you can think of. Integration, not so much. Differential equations, not so much. So the numerical derivatives are going to have their real application in the use of differential equations. We'll also in this section be taking a look at the error terms that are always characterized by the error term of a Taylor series. So we'll end up showing how that comes to play as well. So let's go back to the basics. We are going to look at the definition of a derivative as if you were just taking your first quarter of calculus. And you recall that if you take a function, and you take a function evaluated at some value x and add a small incremental positive value to it and subtract off the functional value without that incremental value and then divide by the incremental value itself, that is the rise over the run. Now you can think about it, the denominator is really x plus h minus x, and the x's cancel out. That's why we get an h in the denominator. So this is a slope. This is a slope between 2 points that are very closely positioned. Theoretically, if you take the limit as h gets really small, that is the derivative. That's the definition of the derivative. But without the limit, we will retain this fractional form and will strategically choose small h values to give us the most precise derivatives we can. Well, you can see right off the bat it's not going to be perfect because anything that's finite, any finite h value, will produce some error. So we are going to have to understand the error at which we're facing. Without the limit, our derivative is exactly equal to this ratio plus a small error if h is small. It's going to be up to us to figure out a formula for that error, and it will be tied directly to the error on the Taylor series. So one thing to notice is that this definition has always been a bit one-sided. We're evaluating the derivative at x, but we're moving away from x in a lopsided manner. You might say, well, why not go the other way? I mean, you could take f of x minus h divided by h. Why wouldn't that be just as good? And the answer to that is it would be just as good. It's just we made somewhat of an arbitrary decision to always go on the high side. Okay, so we're going to need to bound the error, and as I've already indicated, the Taylor error term is going to be that tool that we'll use to bound the error. But first, let's look at a graph. So we're going to start with a very simple function, f of x equals x squared. We're using that because we can figure out the derivative in a hurry. F prime of x is 2x. And so hopefully when we're done, we're going to get something that looks a lot like that. So the blue curve is the parabola f of x equals x squared. And if I choose two values, maybe a low value here and a higher value, I can draw a secant line through those 2 points. Now, if I'm trying to evaluate the derivative at 1/2, which is about where my cursor is pointing right now, halfway between 0 and 1, then if h were somewhat large, f of x plus h would be sitting up here maybe at 1.0. Now that would take an h equal to 0.5, which seems pretty big, but you could do that. And then f of x plus h minus f of x divided by h would be the slope of that red line. Well, if I'd like to do a little bit better, I could perhaps just take the derivative of that point, or I could even take smaller spacings, and I could draw a yellow line that was tangent to the curve at 1/2. Okay, so let's go back to the algebra and see if we can't characterize that error term. So here's our good old-fashioned friend, the Taylor series. So our f of z is going to be f evaluated at some constant position. I'm calling it z sub naught. If I take f of z naught plus the derivative at z naught times the deviation from z, for z minus z naught, that would produce the linear approximation of the Taylor series. Or if I wanted to go farther than that, I could get a quadratic correction term. And I end up taking 1 over 2 factorial, which is just 1/2, times the second derivative evaluated as z0. And I still take the same distance of z minus z0, but I square it this time. So what I am going to do is make a replacement here. Now, so watch this carefully because you didn't do this in your calculus class. What I'm going to do is do a replacement. I'm looking at my formula up here where it looks just like a Taylor expansion, except in terms of z's, which shouldn't be any problem. But now I'm going to declare that my z was really equal to x plus h, and my z naught was equal to x. Now that's a bit different than anything you've seen before. We're not used to things with a subscript like z1 or z2 or z sub 0 to be anything but a fixed number. And now I'm saying, I want to make that an actual variable, the variable x. And I'm relating z and z0 to be quite similar. I mean, these two numbers are clearly close together and related. They both are a function of x. But the Taylor series doesn't care what you put into it. As long as you keep the form right, you can use any arguments that you want. So I am going to dutifully take the x plus h and stick it in everywhere I see a z, and I'm going to take x and stick it in everywhere that I see a z naught. So let's just see what that looks like. So what I end up with is f of x plus h is on the left, and f of x is the first term on the right, because my x and my z naught I've declared to be the same thing. And if I just go through and plug that into the entire Taylor series, I get something that looks kind of ugly, but it's certainly right. It clearly is going to simplify, though, because you've got these terms, x plus h minus x, that repeat themselves in every parenthetical term in the series. And the x's are going to cancel out, and all you'll have left is the h. So let's write that down and see what that looks like. We end up with f prime of x times h plus 1/2 f double prime of x times h squared, and the next term involves h cubed, because every single one of these parenthetical values has the x subtracting against itself, and so it disappears. So we've now simplified this formula, and we have also started developing the pieces of what would be our numerical derivative. So sort of stare at that for a second, because we're going to use this on the next page. The f of x plus h equals f of x plus f prime of x times h plus a bunch of other junk that is the remaining portion of the Taylor expansion. Okay, so let's see where that goes. So here we are from the previous page. So now what I want to do is subtract f of x from both sides of the equation, and therefore get a difference, now a delta, that looks an awful lot like the numerator of my derivative limit. And then you'll notice on the right side, after I make that subtraction, an h appears in every term. Well, it may be an h squared or an h cubed, but there's at least one h in every term of that sum. So I would like to factor out one h and then divide both sides of the equation by h. What will I get? Well, I get f of x plus h minus f of x divided by h is going to be equal to some awful looking balance of the Taylor series divided by h. There's still an h in every term of the numerator. So when I divide that out, that is going to actually go away. So let's do that. We've now divided h on the right side. The left side we're leaving alone. And we now have what looks like a computational form of the derivative, a form that looks just like the definition of a derivative, except we haven't taken a limit. And we're saying that's equal to the true derivative, the exact derivative, plus a bunch of junk that's associated with a Taylor expansion. As h is getting to be small, anything that's a power of h is really going to get small. And the only thing that would go wrong is if these derivatives were just blowing up on you, and that could cause a problem. But most functions, those derivatives are fairly stable. So we could rewrite this expression solving for f prime, and we would say that f prime was just equal to this divided difference here plus an error. So we would call this thing now an order of h error. Here we're saying that the error is almost linearly proportional to h, because the rest of the stuff disappears really fast. When you start getting powers of h, this goes away, especially when you're dividing by a factorial. So it's only the leading term that we really care about, because that drives the vast majority of the error. So what did we get out of this? We got ourselves a computational formula to do a numerical derivative. This first fraction is the term we will use to estimate a derivative, and the beginning portion of the Taylor expansion will be what we will use to estimate the error. So that's where we're going with this finite difference, and of course the convergence speed is going to be directly related to that h value. So that ends section 4.3a on the definition of at least a first order derivative, and we will come back to this on our next session.